A student prepares 100 milliliters of a saturated solution of MgF2 by adding 0.50 grams of solid MgF2 to 100 milliliters of distilled water at 25 degrees Celsius, and stirring until no more solid dissolves. Assume the volume of undissolved MgF2 is negligibly small. The saturated solution is analyzed and is determined the concentration of F- in the solution is 2.4 times 10 to the negative third molarity. Write the chemical equation for the dissolving of solid MgF2 in water. MgF2 dissolves into Mg2 plus 2F-. Calculate the number of moles of MgF2 that dissolved. In the problem, we're given that the molarity of F- in the solution is 2.4 times 10 to the negative third molarity. Molarity times liters is moles, so we convert the molarity of F- in the solution to moles. So 2.4 times 10 to the negative third times 0.1 liters, since there's 100 milliliters, equals 2.4 times 10 to the negative fourth moles of F-. And then using the balanced chemical equation, we use the molar ratio of 1 mole of MgF2 to 2 moles of F-, and we find there's 1.2 times 10 to the negative fourth moles of MgF2 that dissolved. Determine the value of the solubility product constant, KSP, for MgF2 at 25 degrees Celsius. KSP is equal to the concentration of Mg2 plus times the concentration of F- squared. The exponent comes from the coefficients in the balanced equation. Since there's 2 F-, the concentration of F- must be squared. And so that will equal x times 2x squared, which is 4x to the third. So we know the concentration of F- is 2.4 times 10 to the negative third molarity. And since the concentration of F- equals 2x, x equals 1.2 times 10 to the negative third. So the concentration of Mg2 plus equals x, which equals 1.2 times 10 to the negative third. So KSP equals 1.2 times 10 to the negative third times 2.4 times 10 to the negative third squared. So KSP equals 6.9 times 10 to the negative ninth. A beaker contains 500 milliliters of a solution in which both Ca2 plus aqueous and Ba2 plus aqueous are present at a concentration of 0.10 molarity at 25 degrees Celsius. A student intends to separate the ions by adding 0.20 molar NaF solution 1 drop at a time from a burette. At 25 degrees Celsius, the value of KSP for CaF2 is 3.5 times 10 to the negative 11th. The value of KSP for BF2 is 1.8 times 10 to the negative 6th. Which salt will precipitate first, CaF2 or BaF2? BaF2 is more soluble because a beaker contains 500 milliliters of a solution in which both Ca2 plus and Ba2 plus are present at a concentration of 0.10 molarity at 25 degrees Celsius. A student intends to separate the ions by adding 0.2 molar NaF solution 1 drop at a time from burette. At 25 degrees Celsius, the value of KSP for CaF2 is 3.5 times 10 to the negative 11th. The value of KSP for BaF2 is 1.8 times 10 to the negative 6th. Which salt will precipitate first, CaF2 or BaF2? CaF2 will precipitate first because it's less soluble. Since CaF2 and BaF2 both dissociate into the same number of ions, we can compare their KSP values to see which one is more soluble. Since BaF2 has a higher KSP value, that means it's more soluble, and therefore less likely to form a precipitate than CaF2 is. The addition of NaF solution does not significantly affect the total volume of the liquid in the beaker. Calculate the minimum concentration of fluorine necessary to initiate precipitation of the salt selected in parts I. CaF2 dissociates into Ca2 plus and 2F minus. So the KSP equation is the concentration of Ca times the concentration of F minus squared. We are given that the concentration of calcium is 0.1 molar. So KSP equals 0.1 times the concentration of F minus squared. We know the KSP value is 3.5 times 10 to the negative 11th. So 3.5 times 10 to the negative 11th equals 0.1 times the concentration of F minus squared. So the concentration of F minus is 1.9 times 10 to the negative 5th molarity. Calculate the minimum volume of 0.2 molar NaF that must be added to the beaker to initiate precipitation of the salt selected in Part I. For this problem, we use the equation M1V1 equals M2V2. So the new molarity of 0.2 NaF times the new volume, which is what we're solving for, equals the molarity of F minus 1.9 times 10 to the negative 5th times 500 milliliters, the initial volume. And since the addition of NaF is negligible on the total volume, we leave V2 as 500 milliliters. So V1, or the new volume of NaF needed to initiate precipitation, is 4.7 times 10 to the negative 2nd milliliters. There are several ways to dissolve salts that have limited solubility. Describe one procedure to redissolve the precipitate formed in Part B. One way to dissolve salts that have limited solubility is to increase the temperature. Increasing the temperature will cause the equilibrium to shift to the left, therefore producing more products, creating more salt and more precipitation.